Bismillahirrahmanirrahim. Okay, if you have any questions, please ask your questions. Then we will proceed with the remaining part of our lecture. Any question? Are there any questions? Okay, last time we were discussing these bending moments obtained from the direct design method, and then okay, so I will just demonstrate the calculation of reinforcement for one of the bending moments, and the rest you can do yourself. And I will do for the east-west direction column step negative bend, interior negative bending moment, which is this value. So here it is this value, 28.3 foot cap bending moment value. I will calculate the area of steel for this bending moment and the spacing required corresponding to number 5 bar, and then the rest you can determine the reinforcement and spacing yourselves. Okay, so look at this, pay attention to this, please. The bending moment, which is basically MU, because this is effective bending moment, 28.3 foot cap. So we'll convert this into inch cap first of all. Okay, 28.3 into 12 is 339.6. Let's say 340 inch cap. Okay, we will calculate area of steel for this. Let's say we assume small a equal to 1 inch, and we calculate AS for this MU 340 divided by 0.9 Fy into D minus A by 2. D was 8.5, we discussed in the last lecture, minus 1 divided by 2. So we'll calculate area of steel from this. 8.5 minus 0.5, this will become 8. Okay, so 340 divided by 0.9 divided by 60 and then divide by 8 is equal to 0.787 square inch. We will recalculate small a, 0.787 into Fy is 60 divided by 0.85. Fc prime is 4 into 12. Into 60 divided by 0.85 divided by 4 and divided by 12 equal to 1.15 inch. We'll recalculate AS. The difference in 1 inch and 1.5 inch is very small, so the actually will not be too much affected. But let's calculate this value once again. 340 divided by 0.9 divided by 60 into 8.5 minus 1.15 divided by 2.
Sir, 0.85.
G? 0.85 किधर है? Where is 0.85?
सर ये एएस मैंने कैलकुलेट की 0.85 आता है.
नहीं 0.85 कैसे आप दोबारा चेक करें.
ना यस सर ये ट्रायल से ही मैंने की.
फाइनल वैल्यू आप बता रहे हैं. आप वो ट्रायल करेंगे. आपने पहली वैल्यू है?
ना सर नहीं सर ये आप जो कैलकुलेट कर रहे हैं ये मैंने की.
तकरीबन 0.8 की करीब वैल्यू आ जाएगी. 0.8. इसको दोबारा आप डालेंगे तो स्मॉल ए में कोई इतना खास फर्क नहीं आएगा. तो फाइनली द वैल्यू कम्स आउट टू बी 0.8 स्क्वायर इंच. ठीक है. इस तरह से अब आप जब एक वंस यू कैलकुलेट दिस वैल्यू ऑफ एएस फॉर दिस गिवन बेंडिंग मोमेंट व्हिच इज 28.3 फुट किप, this is the value. For the rest of the bending moment, you can use the unit rule. Okay, like this. I will demonstrate this one to you to see how the unit rule is applied. Okay, we have calculated this for 28.3. Let's say we calculate this for 16.8 or 14. Or any other value, this value of 0.28.3 for 28.3 foot kip bending moment, the area of steel comes out to be 0.8 square inch. Okay. So for any other value, let's say for 16 kip, what will be the value? If you can calculate by this 16 multiplied by 0.8 divided by 28.3. Because AS is directly proportional to MU. And everything remains constant, you can calculate this value with the help of a unit rule. Okay. So this is 16 into 0.8 divided by 28.3. 0.45. And so on. For the rest of the bending moments, you can calculate area of steel in this manner. Correct? For all the bending moments, you can calculate now the area of steel using this unit rule for the column strip as well as for the metal strip, because the thickness of the slab is uniform. So you can use unit rule for any of the bending moments. Okay. And since effective D we have taken as average effective D along both the directions, you can use this unit rule for the other direction as well. Once you do this, the next is a decision about the diameter of the bar or the number of bar to be used in this slab. Let's say we want to use number 5 bar. So number 5 bar has an area of steel equal to 0.3 square inch. Okay, you know this. So spacing is equal to area of bar divided by area of steel. Area of bar is 0.3 and area of steel is, let's say, 0.8 into 12. So 4.5 inch.
सोहराब, आप अपना माइक ऑफ कर लें।
So spacing comes out to be 4.5 in center to center for the maximum bending moment, which is 28.3 foot kip in this whole slab design example. All the spacing for number 5 bar shall be greater than this. Okay. So now for the rest of the reinforcement, you can calculate spacing yourself. Finally, you will have to adjust the spacing in such a manner that the placement of reinforcement is finally very conveniently done at the site, okay, without any problem. Now look at the bend moments once again. Bending moment along the east-west direction. Okay, these are the bending moment in the column strip. These are the bending moment in the middle strip. And this is the bending moment in the exterior frame. Okay, we have calculated area of shield according to this bending moment, and for the rest of the bending moments, you can calculate area of shield from unit rule, and finally you can also calculate the spacing once you calculate the area of steel. Okay, then finally you will have to make some adjustment in the spacing. For example, if you look at this 16.8, so 16.8 and 14, they are a very close value. Similarly, if you look at this value of 11.87 and 10 and 9.4 and 11.2, over here we have to calculate only bending moment for one of the value. Sorry, this 11.87, 11.2, and these four values for the negative bending moment: 10, 9.2, 9.4, and 8.8. One of these values. So you have to make some adjustment in this, in so that there is not too much variation in final spacing. माइक ऑफ करें आप लोग, माइक ऑफ करें आप सब, all of you. Please turn off your mics. Please turn off your mics. Turn off your mics, please. Okay, this is along the north-south direction. Same thing. So finally, if you look at the spacing, the spacing variation is not too much, and it is not good from the practical point of view that there are a lot of variation. There is a lot of variation in the spacing of reinforcement, because the placement will become too difficult for the fabricator. So if you look at the spacing, there are only three different spacing. First of all, coming to the negative reinforcement, this is AA. There will be negative reinforcement as stop bars. If you take a cross section of this, so at AA we have negative bending moment, negative reinforcement, we place a stop bars. This is number 5 at the rate of 4 in center to center. We have just calculated this value, and this value was coming out to be number 5 at the rate of 4.5 in center to center. However, we have used the value of we have used the spacing of 4 in center to center here at the column strip negative interior negative bending moments at location A. At location B, the value is number 5 at the rate of 8 in center to center, double of this, because the bending moment was almost double of this. Positive bending moment, if you look at the difference in the positive bending moment and negative bending moment, this value was 16 and this value was 14. There is a difference of 2 foot cap. However, in order to minimize variation in the reinforcement spacing, we also kept this value of number at B number 5 at the rate of 8 in center to center. Okay, this value number 5 at the rate of 8 in center to center, correct? And at any other location at C, this value is number 5 at the rate of 12 in center to center. Here also number 5 at the rate of 12 in center to center. So such kind of adjustment will be important, especially in the positive reinforcement, because in the positive reinforcement, the bar will be placed. For example, for this B positive reinforcement, the bar will be placed and from like this. When these bars enter into another panel, then these bars shall be placed in such a manner that there is no problem in placement in the adjacent panel. For example, if we place number 5 bars at the rate of 8 inch center to center in the first exterior panel. Okay, and in the interior panel, the spacing is number 5 at the rate of 12 inch center. How are we going to achieve this? What we will do is that we will cut one bar like this, number 5 at the rate of 12 inch, 8 inch center to center in the first interior strip, and we will cut this one bar. Again, we will continue the two bars will be continued and one will be cut here. So the spacing between the two will become number 5 at the rate of how much? 16. Now we will cut two of them like this. So I'll try to demonstrate this in another. For positive, negative reinforcement, if you take a section, first of all, let me show a section. If this is a section of one of the column strip, let's say. And so on. So a negative reinforcement we placed here. This is number 5 at the rate of number 5 at the rate of 4 inch center to center. And this will be extended up to L by 3 on both sides, L by 3. The spacing is different in the negative reinforcement. So it has nothing to do with the spacing at any other location of the negative reinforcement, because the reinforcement will be curtailed and it will be placed as stop bars. So this reinforcement spacing has nothing to do with this reinforcement spacing or this reinforcement spacing. Okay, but in the positive reinforcement, apart from the convenience in the placement of reinforcement for a fabricator, there are practical issues. For example, let's say we want to place reinforcement like this. So if the reinforcement here is number 5 at the rate of 8 inch center to center, and here it is number 5 at the rate of 12 inch center to center, how are we going to achieve this? Okay, in plane, if you look at this, if spacing here is number 5 at the rate of 8 inch center to center, how can you achieve this number 5 at the rate of 20 center to center when you enter into another panel? So you must have to look into this. Okay, this spacing is 8 inch. If we cut these two bars, this 8 and 8, this will become, and we extend this, so this spacing is now 24 inch. We'll place another bar like this here to make this 12 inch. So the spacing is now 12 inch. So we'll continue these two bars, we'll cut these two bars, so that the spacing is achieved with the desired spacing. So this kind of adjustment must be kept in mind while finally, when final decision on the spacing is made for the preparation of drawings and onward use at the site. Okay. Same kind of exercise can be repeated along the north-south direction. Once this is done, there are some recommendation of the ACI code for two-way slabs. Okay, these are the recommendations like this. That the maximum spacing and minimum reinforcement criteria according to the code is such that maximum spacing shall not exceed twice of the thickness of the slab. This max must be less than 2 HF or equal to 2 HF. Okay, and in this case, HF is 10 inch, so maximum spacing cannot be more than 20 inch. At the same time, minimum reinforcement shall also be checked at the critical location. Minimum reinforcement in this case is 0.0018 times 12 times 10. So if you calculate this, this comes out to be at all critical locations. Critical locations are positive bending moments at the midspan and negative bending moments at the supports. This comes out to be 0.216. 0.216. So you calculate this minimum reinforcement in the beginning and then proceed with your calculations. Okay. Then the 3 by 4 inch cover, you know this very well, for negative as well as for positive reinforcement shall be maintained everywhere. This is for fire protection and corrosion protection. Okay, reinforcement placement, how the reinforcement shall be placed. This is important to note. You should pay attention to this. In the case of two-way slabs supported on beams, short direction bars are normally placed closer to the top or bottom surface of the slab with a larger effective depth because of greater movement in short direction. You know this when there are beams in the slab system, two-way slabs with beams, then bending moment along the short direction will be more than the bending moment along the long direction. And for this reason, we prefer placement of reinforcement to be closer to the bottom or top side along the short direction in order to provide more effective depth. However, in the case of two-way slabs without beams, this is exactly opposite of this. Because the bending moments, if you look at the bending moments, all the bending moments that we have calculated in this example, the bending moments along the long direction are more than the bending moments along the short direction because the behavior is totally different. The behavior of two-way slabs without beams is totally different from the two-way slab with beams. Okay, because all the bending moments shall be registered by the slab alone. For this reason, the bending moments, when the bending moments are larger than the bending moments, when the bending moments are larger along the long direction than the bending moments along the short direction, the bars shall be placed closer to the top and bottom side of the slab along the long direction instead of short direction. Okay. Next is splicing. When it will be very frequently required that the two bars shall be lapped somewhere, especially in the positive reinforcement along the length of the slab. So whenever splicing or lapping is required, it shall be done according to the code requirements, ACI 8.7.4.2.1. And there are two requirements for this. The splicing shall be avoided at the critical location. For positive reinforcement, splicing shall be avoided at the midspan of the slab, and it shall be done somewhere at towards the ends of the slabs. Okay, and whenever this splicing is done, this shall be equal to the requirement of the lap length requirement of the code, which is generally for a grade 40, for a grade 60 steel with 4 KSI, it is equal to LD 47 dB. If you round this up, it will be around 50 diameter of the bar. Okay, bar number 7 in larger bar. You know this. We have done some calculations on this. You can calculate the development length requirement, and then the lapping can be done according to that requirement. Okay, continuity of bars. The ACI 8.7.4.2 are also required that at least two of the column strip bottom bars in each direction must pass within the column core and must be anchored at exterior supports. These bars shall be these bars of the column strip. Basically, these are the column strip positive bars. The positive reinforcement of the column strips shall be provided in each direction such that two of these bars must pass through the column core. The column core means the area of the column enclosed by the stirrups. So it means that the area of the column outside the stirrup, which is basically the cover, is not included. So within the column core, two bars must pass. Okay. Then the cutoff bars, negative and positive reinforcement. Negative reinforcement shall be curtailed at 1/3 of the length of the span. Okay, and the positive reinforcement shall be continued from one span to another span according to the spacing requirements, like this. Okay. There is another requirement which is common to both slab with beams and without beams, and this is a requirement due to the torsional stresses These torsion stresses occur in corner slabs. Reinforcement should be provided at exterior corners in both the bottom and top of the slab for a distance in each direction from the corner equal to 1/5 the longer span of the corner panel as shown in figure. The positive and negative reinforcement should be of size and spacing equivalent to that required for maximum positive moment per foot width in the panel, according to ACI 8.7.3. So this is the positive and negative reinforcement shall be provided in this manner, okay, which is basically this must be placed to L by 5 of the panel size, and this shall be equivalent to the required maximum positive. Whatever the maximum positive reinforcement is, this reinforcement shall be equal to this, both positive and negative. If negative is more than this, then it is fine. But if it is less than this, it should be at least equal to the positive reinforcement spacing provided here at this location. Okay, this is a homework for you. This is the same slab panel with the same sizes, only the loads have been changed. You are required to analyze the slab supports a live load of 60 pounds per square foot. Superimposed dead load is given, which is different from the previous example. Column sizes are same, but the material strength are different. FC prime is 3 KSI and FY is 40 KSI, unlike 4 and 60 KSI in the previous example. Okay, this is a calculation summary. Slab thickness is the same. Factor load is this. Column strip width is 5 feet. Okay, and these are the bending moments. So the bending moments are given to you. If you want to compare your results with these bending moments, you can do this very easily without any problem. Okay, and finally you can design this as well. These are moments per strip width. Okay, these are the bending moments along the north-south direction. So you can practice this, and then you can compare your results with those given in our presentation. And also you can try designing the slab panel, assuming number 5, number 4, or number 6 bar. Okay. Then there is another example where the dimensions are different. This time the dimensions are 20 by 15 feet, and the slab live load is 60 pounds per square foot. Superimposed dead load is 40 pounds per square foot. Columns are 12 inch square. FC prime 3 and 40 KSI are given in the example. You can also practice this. Okay, again the final values are given for the purpose of comparison. You can practice it as well. This will enable you to improve your understanding of the direct design method and to build your confidence in solving the problems. Summary of the direct design method. You have seen that in the direct design method, we first of all select the size of the slab and columns. The slab depth can be calculated from ACI table, and then we find load on the slab. On given column plane of building, we mark location and dimension of all frames. For a particular span of frame, we find static movement equal to WUL 2ln square divided by 8. Then the longitudinal distribution of static movement is carried out according to the coefficients given on this slide. A lateral distribution is also done then according to the coefficients given, and the remaining moments goes to metal strips, and we design and apply the reinforcement requirement with the maximum spacing should be less than or equal to twice of the thickness of the slab. So this was all about the session 1, the flexure design of flat slab and flat slabs. Then there is the next session on the shear design for 2 slab system without beams. If you have any question, you can ask your questions now. Okay, otherwise we will go ahead with the remaining part of the lecture on session 2. Any questions? Please, you can just tell me your name and ask your question. If there is any.
Excuse me, sir.
Please.
Sir, this is Farooq Ahmed, sir. We have designed column, beams, and footing so far, sir. But we haven't learned about the joint at column and footing beam and column. So, any discussion
Okay.
on these joint?
Yes. Okay. Very true. Uh, Not only these connection which you call is joints, but many other things we've also not covered in this lectures, and we cannot do this because this is a reinforced concrete design 2 course, and many other things are not covered in this lecture. There are many other systems which are not covered because this is a second beginner level course. We have already covered one course which was very initial level. This is a little bit advanced level than that, but still there are many things which we cannot cover in this uh, course. And these remaining things are then covered in our master courses. Okay, so the connections, these are called connections. These connections are covered, but then there are a separate full lecture on the connection. And you can realize the importance of connections from the fact that there is separate code for connections. The ACI 318 does not cover the design of connections. There is separate code for the design of connections. And we do this in our master courses. So you are very right that we have not discussed anything about the connections. We cannot do this at this stage. Okay. Any other question? Any other question, please? ये हमारे दोनों कोर्सेज जो हैं RCD1 RCD2 के, इसमें हम बुनियादी जो चीज़ें हैं डिज़ाइन के हवाले से उसको हम पढ़ रहे हैं और साथ साथ हम ACI कोड भी डिस्कस कर रहे हैं। तो इसमें बहुत सारी चीज़ें ऐसी हैं कि जो हम डिस्कस नहीं कर सकते क्योंकि ये कोर्स हमारा बहुत लंबा हो जाएगा। पहले ही से ये कोर्स काफ़ी इसका जो कंटेंट है बहुत ज़्यादा है, तो इसमें और चीज़ें शामिल करने की गुंजाइश भी नहीं है। लिहाजा इसमें ये RCD1 और 2 जो है ये आपको कंप्लीट पिक्चर डिज़ाइन का नहीं दे सकता। इसमें बहुत सारी चीज़ें ऐसी हैं कि जो आप आगे फिर पढ़ाते हैं मास्टर कोर्स में, और मेरे वेबसाइट पर हमारे मास्टर कोर्स का पूरा जो कंटेंट है और लेक्चर्स हैं वो सारे पड़े हुए हैं। उसमें कनेक्शन पे पूरा अपना एक लेक्चर है और वो उसका कोड भी डिफरेंट है। इस तरह और भी बहुत सारी चीज़ें हैं जो हम इसमें कवर नहीं कर सकते, और स्टिल MSc के उस जो RCD2 का लेक्चर उसमें भी बहुत सारी चीज़ें रह जाती हैं क्योंकि रिइंफोर्स्ड कंक्रीट डिज़ाइन के बिल्डिंग डिज़ाइन में काफ़ी सारी चीज़ें होती हैं जो प्रोजेक्ट टू प्रोजेक्ट वेरी करती हैं, और बेसिक कॉन्सेप्ट जो हम सीख लेते हैं तो उन चीज़ों को फिर सीखना आसान हो जाता है। ठीक है। Okay, if there are no questions, then let's proceed with the second part of this lecture on session 2, design, shear design. These are the most common types of two-way slab systems. On the left, we have flat plate system, and on the right, we have flat slab system. The only difference is that in the vicinity of the columns, when a drop panel or column capital or both of them are provided, then the flat plate is called as flat slab. This is the difference. This is just for the sake of terminology to differentiate between the two systems. One is called as flat plate, another is called a flat slab system. Okay. The most common problem in the flat system is that the punching shear problem. Okay, when two-way slabs are directly supported by columns, shear near the column, which is called as punching shear, is of critical importance. And therefore, in addition to flexure flat plates, shall also be designed for two-way shear, which is called as punch-out shear stresses. Unlike slab with beams, in slab with beams, the columns are provided generally on the columns on the beam center line, and beams have sufficient depth. Therefore, the punching is basically a problem when column tries to punch the slab. This is just like a piece of paper supported on the paper pins. When a piece of paper is supported on paper pin, then paper pin can make a hole in the piece of paper. So this is called as punching. So the thicker the piece of paper is, the difficult it will be for the paper pin to make a hole in the piece of paper. So in the same manner, either we should increase the overall thickness of the slab, or we should increase the thickness of the slab in the vicinity of the column, which we call as drop panel. This will minimize the problem of punching shear. What else we can do is to increase the head of the paper pin. For example, if we increase the head of the paper pin, then still it will become a little bit difficult for the paper pin to make a hole in the piece of paper. In the same manner, we increase the size of the column at the head of the column where it supports the slab. So then it is called as column capital. So either column capital or drop panels, one of these are simultaneously at the same time. Both of these can be provided in order to minimize the problem of punching shear. In this animation, we have tried to explain this problem of punching shear. Okay, you should pay attention to the making of hole. The point that is important, that unlike the piece of paper and pen example, where the pen make a hole in the piece of paper, and this hole is made at the edges of the paper pen. Okay, for example, let's say if this is a paper pen, and this is a piece of paper, so this crack or a hole will be made vertically like this, okay, at the edges of the paper pen. But in the case of a reinforced concrete slab cast monolithically with the column, this crack will not occur here. This crack will occur at the angle of 45 degrees, somewhere like this, okay, more or less. And which means that this part of the slab, which is, now I'm going to mark this part of the slab, this part. This part of the slab will be separated from the remaining part of the slab, and this slab part will be like this will become like part of the column. This will remain on top of the column, and the remaining part of the slab will crack and may fall down. So, which means that the punching will not occur at the edges of the column, rather it will occur at the angle of 45 degree. Okay, so if we want to calculate the shear load which is causing the separation of the slab, okay, so basically it is this load on this hashed part, this load, and this load is causing this shear, because this remaining part, this will not take part in the this load is directly coming to the column. This load is directly coming to the column. So if you once again think on the example of needle and piece of paper, so it is basically the weight of the piece of paper that is causing the paper pen to make a hole. If this piece of paper is very, very light, then probably the paper pen will not pass through the piece of paper. It will depend on the weight of the piece of paper. The heavier the piece of paper is, the easier it will be for the paper pen to make a hole. So it is the weight of the slab that is going to cause this punching shear. Which part of the slab is causing this shear? This hedged part of the weight slab is causing this shear, not the whole part. So whenever we want to calculate the demand on the demand punching shear, this punching shear should calculate this part of the slab, not this part of the slab which is directly going to the column. Okay. I think if you remember, we discussed this while you were designing the isolated column footing. We discussed this. We'll quickly go through this. This is the punching out column. Okay. So this part of the weight is causing this weight of this part of the slab is causing this punching shear. And this crack occurs at a distance of d/2 from the face of the support. d/2 from the face of the support. critical shear is taken at a distance d from the face of the support in the case of beam shear, or in the case of punching shear, it is taken at a distance of, this is beam shear. And in beam shear, you know, we take critical shear at a distance of d from the face of the support, not this maximum shear. So we calculate this Vu here at the distance d, and we do our designs for this critical shear, which is the distance of d from the face of the support instead of the maximum shear. In the same manner, we will calculate shear at a distance of d by 2 now for the punching shear for this green area. So the method for this is that you calculate the total slab load and then deduct this small area from that, and this will give you the punching shear demand. Like this. So there is a demonstration to this now. Okay. How we deduct this area? First of all, we need to know the dotted line parameter. The dotted line parameter is critical parameter. You know this. This is called as critical shear parameter B0, and this is this all the sides 2CS1 plus D plus 2CS1 LD, and this is B0 critical shear parameter. And when this critical shear parameter is multiplied with the thickness, this will give you that area. For an H column, this critical parameter area is this side, and only this one side. So this will be 2CS1 plus D2, D by 2, and C1 plus D. This is C1 plus D, only one. For a corner column, this will be C1 plus D by 2, and C1 short side, S means short, and C1L long side plus D by 2. L1, L2 will occur like this. Punching shear demand for an interior column is demonstrated here in this slide. B0 is equal to 4 into C plus D. So the total vertical load which is causing, which is the weight of this total slab, must be equal to L1 into L2 into the per square foot load on this slab. However, for the case of punching shear, we will deduct this load. We will deduct this part. The green area, if you want to calculate the weight of the green area, then the total weight must be deducted. The total weight minus this load will give us the green area load. So this will be L1 into L2 minus C plus D whole square divided by 144 if these are in inches. So this will give you this green area. Once this green area is calculated, you can calculate punching shear from this VWU into A T, which is the area contributing to the load. Okay, once the demand shear is calculated, then the capacity of the slab in punching shear is calculated from 5Vn is equal to 5Vc plus S. We know this. And 5Vc is least of 4Fc prime B0 D, 2 plus 4 divided by beta C. These are three equations. And the least of this will be taken. What is beta C? In this equation, beta C is longer side of column to shorter side of column. For square column, this is equal to 1. And alpha S, 40 for interior column, 30 for H column, and 20 for a corner column. Okay. Most of the time, first equation will give you the least value. Okay, there is a requirement of ACI code. When 5Vc is greater than Vu, then nothing is required. Unlike the beam shear requirement, where when 5Vc by 2 is greater than Vu, then nothing is required. Here, in the case of punching shear, if only 5Vc is greater than Vu, then nothing is required, which means no increase in slab thickness or other things. When 5Vc is less than Vu, what should we do? Okay, whether we should provide some kind of stirrups or what? Okay, when 5Vc is less than Vu, then we have several options. Either we increase depth of the slab in order to increase 5Vc. Okay, so if we want to increase the overall depth of the slab, it will increase the weight of the slab as well, and it will further create problems for us. So in order to avoid this further increase in our problems, we would increase the depth of the slab in the vicinity of the column, and that is called as drop panel. The other thing is, the other option is that we increase the area of the column. So if we increase the area of the column, or the size of the column, all along the length of the column, then again it will create problems for us instead of reducing our problems. So what we do is that we will increase the area of the column at the head of the column, where the column is supported on the where the slab is supported on the column, and that is called as column capital. Or we do both of them. We can also increase the concrete strength, but this is also not a good option. Maybe a good option in some cases, but in most of the cases, it's not a good option because it will unnecessarily increase the price of our project. If all these options cannot be explored or provided due to some reason, then we will provide reinforcement. Reinforcement can be provided in 4 ways. The most common is providing an integral beam. Integral beam is a beam which will be placed inside the slab so that it is not projecting out of the slab like this. If you want to see this in a section, so it will look like this. This will be a beam contained within the slab, okay? And this will not run from one column to another column. This will be placed on top of the column in this manner up to a certain length, which will be calculated in one of the examples. And then the strips will be provided in this manner along both the direction. The strips will be provided in this manner. Okay, this is called an integral beam. This will reinforce the slab in the punching shear, and it will also shift the critical shear parameter away from D/2 location. This is another option, which is basically bending of flexure reinforcement in this manner at the locations where the crack is expected. You have seen that crack is expected at a location of D/2 from the face of the column. So if we bend these bars in this manner, the bending of the bars and the number of bars must be calculated in a proper manner. Third is providing shear heads. Shear head is steel sections. I sections most probably an I section will be placed. One I section will be placed from end to end, and the other section will be welded to this in this manner. This is, if you want to see, this is an I section. Again, this I section will be contained within the slab. Okay, it will not be projecting out from the slab. So this is one I section, and the other I section is welded to this. Is called as shear head reinforcement. And the fourth is a shear stud reinforcement, which will be provided in this manner. A shear stud, a typical shear stud strips with nails is shown in this figure. Again, this will be calculated in a proper manner, and this can be provided in this manner in the plane. This is a plane, and this is a section of this. Most probably we provide, most frequently we provide this integral beams because we have reinforcement, a lot of reinforcement is available at the site. Okay, some of the lengths are already there at the sites as a wastage, and we can utilize those bars as integral beams. And so this is the easiest way of reinforcing the slabs against the punching shear. Then, okay. If you want to provide drop panel, then there are requirements for drop panel as per ACI code. According to the ACI code 8.3.11.1 and 8.2.4, this places 2 requirements. One of the requirements is that the size of the drop panel should be at least L/6, L/6 in both directions. L/6, L/6 from the center of the column. Which means that, for example, if this length LB and this length be, let's say 30 feet. So 30/6, 5 feet and 5 feet on both sides. The size of the drop panel shall be at least 5 feet on one side and 5 feet on the other side. So this will be basically 10 by 10 feet drop panel in plane. and the thickness of the drop panel shall be at least 1/4 of the slab thickness, the remaining slab thickness. So, which means that, for example, if this slab thickness is 10 inch, then the drop panel should be at least 2.5 inch. 10 divided by 4, 2.5 inch. If this is 12 inch, it should be at least 3 inch. It can be greater than this, but this is the least requirement of the code. These are two requirements for the drop panel. The requirements for the column capital. There are two requirements for the column capital. One is with regard to the angle at which the angle from the vertex at which this column capital is provided. The maximum angle from the vertical is 45 degrees. From the vertical line passing through the column central line, this angle of the column capital shall not be more than 45 degrees. It can be less than this, because if this angle is more than this, it will create problems of the kind of cantilever action. So this angle cannot be more than 45 degrees. The second requirement is that whenever a column capital is provided, the concrete of column capital in the slab must be provided at one and the same time. So form work shall be designed in such a manner that column capital and slab concreting can be done at one and the same time. Which means that, for example, if this column capital is to be provided, then concrete in the column shall be poured up to this location, and then a form work shall be designed in this manner that this column capital can be placed. That concrete in the remaining part, along with the column capital and slab, can be poured at one and the same time. Okay, the requirements in the case of integral beam. If integral beam is to be provided, then there are two requirements of the ACI code. Number one is that there shall be a slab thickness of at least 6 inch effective depth. If effective depth of the slab is less than 6 inch, which means that if total overall depth is less than 7 inch or 7.5 inch, then integral beam will not work. Integral beam will not work in that condition. So the minimum slab thickness shall be at least greater. The slab thickness shall be more than 7 inch in order to work in order to provide this integral beam. And this integral beam will be effective only if the slab thickness is more than 7 inch. Okay, according to the ACI code, this cannot be provided for slabs with thickness less than 7 inch. Overall slab thickness effective D 6 inch. Okay, and when these bend bars or integral beams are to be used, then within the calculation 5EC shall be divided by 2. Okay, 5EC shall be divided by 2. Okay, now coming to the integral beam requirements. The integral beam, if we are providing integral beam, then there are two main components of the integral beam. One is length of the integral beam, and the other is the vertical stirrups. Okay, and how are these going to be provided? Let's see. The vertical stirrups will be calculated. The vertical stirrups are used in conjunction with supplementary horizontal bars radiating outward in two perpendicular directions, both to form what are termed integral beams contained entirely within the slab thickness. In such a way, critical parameter is increased in this manner. Vertical stirrups. Okay, you know that in the case of beam shear, we provide a two-legged vertical stirrup, and we multiply the area of bars with 2 in order to calculate the area of 2 legs. Okay, there are now at every location there are 4 stirrups provided. For example, if we look at this location, then we have 2 legs here, 2 legs here, 2 legs here, and 2 legs here. So there are 8 legs, basically 8 legs for 4 stirrups provided at the same location in the slab in the 2 dimensions, in 2-dimensional environment. Okay, so for the 4 sides, total vertical stirrup area is 4 times the individual 2-leg vertical stirrup area. So if we want to use 3/8 bars, then 3/8 bars is an area equal to 0.11 square inch. This must be multiplied by 8. So the area of stirrups at one location will be 0.88 square inch. how much should be the length of the horizontal bars LV? Let's say from the center of the column, if this length is LV, then this how to determine this LV? LV can be determined using critical parameter B naught. According to the ACI code, distance from the face of the column to the boundary of critical parameter. This is the boundary of critical parameter. This figure is given in the code. From the face of the column to the boundary of critical parameter is 75% of LV minus C by 2, okay, which is 3 by 4 LV minus C by 2. This distance from the center of the column to the end of the bar is LV. So distance from the face of the column, to this end will be LV minus C by 2. And 75% of this 3 by 4 into LV minus C by 2 will be taken as the distance of the critical parameter. Okay, if we now look at this triangle, this triangle has a two sides which are equal, and this is diagonal. Okay, this is taken out. It is two sides equal to x, which are both of them are equal to 3 by 4 LV minus C by 2 and 3 by 4 LV minus C by 2. So this R, which is the diagonal of this triangle, is equal to R square is equal to x square plus x square. Okay, and we can calculate R from this. Once this R is calculated, we can calculate the B naught. B naught is now this dotted line. B naught has been shifted outward from this location. From previously, the B naught was at a distance of D by 2 from the face of the support. Now, with the integral beam, B naught has been shifted outward. So, in order to calculate this B naught is one this side, the second side, third side, and fourth side. So, B naught is basically equal to 4R, 1, 2, 3, 4. 4R plus this side, and this is equal to the column size basically. This is C. This is equal to C. So, this will B naught will be equal to 4R plus 4C. B naught will be equal to 4R plus 4C. Okay, and we need to determine only R. Once we do this, we can calculate LV. For a square column, B naught is equal to 4R plus C, and R is from this, R is equal to square root of x square plus x square, which means square root of 2x. R is equal to square root of 2x, square root of 2x. Okay. Then we have B naught is equal to 4 into square root of 2x plus 4c. Putting value of x is equal to B naught is equal to this thing. After simplification, we get B naught is equal to 4.24 LV plus 1.88 c. And from this, now we can calculate LV. Because B naught will be known to us. The B naught value which we obtained in the beginning will be used in this equation. Okay, and C is the column size. This will be demonstrated in the next example. Okay, let's say we calculate punching shear for a interior column, this one. B naught is equal to 4 into C plus D, so 14 is the column size, 8.5 is this, 90-inch tributary area, excluding area of B naught. This is L1 into L2, and this is C plus D whole square divided by 144. So the area, green area is 496.5 square feet. Punching shear demand WU is equal to 0.3804. VU is equal to WU into AT, and this comes out to be 189 now. Okay. Punching shear capacity. FC prime, square root of FC prime B naught D is common to all the three equations. So first of all, we will calculate this 4,000 square root 90 into 8 divided by 1,000 to convert this into kips. then multiply by 5EC's list of 54FC prime B naught D, which gives us a value of 145 kip. The next gives us a value of 216 kip. The third gives us a value of 208 kip. Okay. Therefore, 5EC 145 kip is the least of these values. We will pick up this value. And since 145 kip is less than 189 kip, which is the punching shear demand, so something is to be done in order to strengthen the slab against the punching shear of 189 kip. Shear design is required. Let's say we decide to provide a drop panel. So in drop panel, the slab thickness in the vicinity of the column is increased to increase the shear capacity, which means the B naught is to be increased. The increased thickness can be computed by computing VU to 5EC and simplifying the result equation from D to calculate H total in this manner. P will equate VU to 5EC, and we know that VU is 189 kip. 5EC 0.75 into 4, these are kept as constant. Okay, B naught will keep as it was in the beginning for the initial thickness of 10 inch, but D we will calculate. What is the required D? H total, therefore, comes out to be 11. If D is effective D comes out to be 11.07 inch, then D plus 1.5 should be at least 12.6 inch. In order to make 5EC equal to VU. So this is very simple. In this simple manner, you can provide the drop panel. This gives us 2.6 inch drop panel. If we want to keep slab equal to 10 inch thick, as it was assumed in the beginning, and the ACI requires 10 by 4, at least 2.5 inch thickness, 25% of this. So 2.7 inch, 2.6 inch thick is enough. This will be provided in this manner: L by 6 on both sides. 25 by 6 is 4.25 feet, and 20 by 6 is 3.5 feet. So 4.25 multiplied by 2, 8.5, and 3.5 multiplied by 2 is 7 feet. 8.5 feet on one side and 7 feet on the other side, and 2.6 inch thick drop panel will be provided. Okay. For the remaining edge columns and corner columns, you can calculate the size of the drop panel yourself. Column capitals now for an interior column. In the case of column capital, we will keep effective D equal to 8.5 inch, and instead we will calculate now B naught. B naught comes out to be 117.2 now. And we will, if we want to keep 5EC equal to VU. Now B naught is equal to 4 into C plus D. So we will calculate C now, which is the size of the column from this equation. Because we know D is equal to 8.5 inch, we are not going to increase thickness of the slab. C comes out to be at least 21 inch. And we know that our size of the column is 14 inch. So 21 inch column, either we provide along the length of the column, either we should increase the size of the column all along the length of the column, or we should increase the head of the column. So we will increase the head of the column in this manner. In order to fulfill the criteria of the ICI code that this angle shall be not more than 45 degree, and we will calculate the requirement of the column is this 21 inch. Total is 21 inch. So this is the size of the column at the head of the column, 21 inch at least. Okay. From where it should start now, the column capital, the starting point of the column capital will be calculated from this angle. So basically, we will calculate this Y depending on this angle. Knowing that one of the side of this triangle is 3.5 inch, because the size of the column is 14 inch. So 21 minus 14 is 7. 3.5 inch is on this side and 3.5 inch is on this side. So the Y can be calculated depending on the angle. y is equal to 3.5 divided by tangent theta. Let theta is equal to 30 degree, then y is equal to 6.06 inch. If you want to keep theta 20 degree, then y is equal to 9.62 inch, and so on. Okay. So drop panel and column capital can be provided in this manner. Let's say now we calculate the integral beam. The integral beam can be provided in this manner. 5EC, we know that 5EC is 145 kip. Okay. When integral beams are to be used, we will reduce 5EC by 2. Therefore, 5EC is equal to 72.5 kip. If we use a half-inch round bar with two legs, 0.4 square inch, there are 4 sides, so the area of steel will become 1.6 square inch. As I said earlier, that for a number 3 bar, the area will multiply by 8 because there are total 8 legs along both the directions and both the side of and on both sides of the column. For a number 4 bar, the area of steel is 0.2 square inch. 0.2 divided multiplied by 8 is 1.6 square inch. The spacing will be calculated. Phi AVA phi D divided by VU minus phi VC. Phi is 0.75, AV is 1.6, and if phi is 60, D is 8.5, VU is 189, and phi VC is 72.5 when it is divided by 2. So this gives us a spacing of 5 inch. The maximum spacing allowed as per code is D by 2, so it is 4.25 inch. We will provide this stirrups at the rate of 4 inch center to center, and using number 4 two-leg vertical strips at the rate of 4 inch center will be enough. The next thing is to calculate the length of these integral beams. The length of the integral beam can be calculated from this equation, which we derived in the previous slides. B naught is equal to 4.24 LV plus 1.88 C. Okay. And B naught that we used in our calculations, the minimum B naught is 117.2 inch. So this 117.2 inch will be used in this calculation. Here, 117.2 inch, 4.2 for LV plus 1.88 cc is the size of the column. This gives us a LV equal to 21 inch. We will round this up and we will use 24 inch, which means 2 feet on one side and 2 feet on the other side of the column. So the total length of this integral beam will be like this. Now 4 feet long integral beams on top of the column will be used with spacing of strips at the rate of 4 inch center to center in this manner. First step will be placed at 2 inch from the face of the column, and the rest of the spacing can be calculated. This is a summary of the whole lecture, that DDM, which we discussed in the beginning of the lecture. This is on the shear critical parameter A1, A2, and then the 5EC. This is the end of this lecture. If you have any questions, you can ask your questions now. Otherwise, I will give you some work for practicing, and then we can discuss this. I will advise that you practice the homework that we have made part of this lecture, and we discuss this. And if you have any question, you can ask questions. Okay, I will give you a break now, and after the break, we'll discuss this. Once again, I will prefer that you practice these examples which are given in these slides. Here, this example, I think this is a good example. If you want to practice this, we can discuss this while you practice this. We have 1 more hour, so you can practice this if you want to ask questions. First of all, let's take a break and then we will see. Okay, 15 minutes break.